Welcome back to the next video, everybody. Today we're going to continue looking at the proof of proposition 4 on how the sizes of congruence modules grow as the corresponding sets of primes grow. This will be part 7 of that. Today we're going to be looking at part 1 of 2 of the proof of theorem TH from a previous video, so let's get into it. So what did we just do? We just, last video, finished proving the following immediate consequence of propositions 3 and 4, which we called corollary CC. If sigma and sigma prime and sigma sub rho bar, where rho bar is kind of our plausibly modular representation, are finite sets of primes, and if f is in n sub sigma, and that's a new form with coefficients in our discrete valuation ring O we've been working with, then the cardinality of h1 sub sigma prime of q add 0 rho f tensored up to k mod O divided by the cardinality of h1 sub sigma of q of add 0 rho sub f tensored up to k mod O, that's less than or equal to the cardinality of the congruence module eta sub sigma mod the congruence module eta sub sigma prime. Okay? So, you might ask why we're continuing to talk about that corollary, which was a corollary to proposition 4, if we're done with it. Well, there are two gaps in the proof of proposition 4 to fill in: theorem TH from video 11.12 and lemma ihara from the previous video. So we're going to look at the proof of theorem TH in this video and in the next video. In this video, we'll just be summarizing the steps of the proof. Let's recall that L sub t is the Tate module T sub L of the Jacobian J0 of n tensored up to O localized at M, and L sub h is the cohomology group H1 of x0n, comma O localized at M, where M is a maximal ideal of the Hecke algebra T sub O generated by the Hecke operators on S2 of gamma 0 n corresponding to some new form F. Recall that the result to be proven, theorem TH, is the following. It very simply says that the T sub sigma modules L sub t and L sub h are free. Okay? I don't know that I said this explicitly, but you can assume that the representation attached to M, rho sub m, is irreducible, and that either L doesn't divide n or L squared doesn't divide n, and the Hecke operator T sub L isn't in M. The reason you can assume this essentially boils down to the fact that these assumptions are always satisfied by Galois representations attached to semi-stable elliptic curves over Q, for example. The reason for that is if T sub L is in M, then A sub L of E is in M, because T sub L acts like A sub L of E. However, A sub L is plus or minus 1 in the case of multiplicative reduction, so that can't happen. All right, so let's get into the proof of this. Again, we're just going to be summarizing the key steps today. Well, we'll make some reductions, and then we'll summarize the key steps, and then we'll give the proof of the key steps next video. So first, LH and LT are isomorphic as T sub m modules, but we know there's an isomorphism between T sub m and T sub sigma. That was kind of a key theorem we had, and so it suffices to prove that one or the other is free, and we'll just prove that L sub t is free. Reducing further, it suffices to show that the localization of the Tate module T sub L of J0n at M intersect T sub Z sub L is free. That is, you can replace O by the L-adic integers and M by the corresponding intersection, and just analyze T sub L of J0n localized at M. Okay? Since this Tate module tensored up to Q sub L over Z sub L is free of rank 2 over T sub Q sub L, that's just basic properties of Tate modules. It suffices to show that the dimension of LT mod MLT as a T mod M vector space is 2. The reason it suffices to show that is as follows. If this dimension is 2, then Nakayama's lemma guarantees us a surjection alpha from T plus T to L sub T. If you tensor this map with any homomorphism from T to Q bar sub L, you get a surjective linear map between two vector spaces of the same dimension, which then has to be injective by basic linear algebra. Well, that means the kernel of alpha here is killed by a power of L, but T sub m is torsion-free, and so that means the kernel of alpha is trivial, and so alpha is injective, which is what we're trying to show. Okay, so let's get into this. You can keep reducing, actually. So T sub L of J0n mod L of T sub L of J0n is isomorphic to the L torsion of J0n, which is isomorphic to FL homomorphisms from the L torsion of J0n to FL as TFL modules. And so if you keep that in mind, then proving that this dimension up here is 2, which is what we've discovered is all we need to do, boils down to proving the following special case of Theorem 2.1 in Weil's paper, which I'll call Theorem 2 dim. It says, let M be a maximal ideal of T sub Z sub L, and suppose that rho sub M is irreducible, and that either L doesn't divide N, or L squared doesn't divide N with T sub L not in M, the usual assumptions that we've already made. Then the T sub Z sub L mod M dimension of J0N bracket M is the same as the TZL mod M dimension of J0N bracket L mod M, and that is 2. Okay? So that follows from the reduction we made on the previous slide and this observation up here. All right? So we just have to prove that. There are 2 cases, though. There's the case where L doesn't divide N, and there's the case where L squared doesn't divide N, but T sub L isn't an M. So we'll look at the first case first. This is easier. We will need a fact about Fontaine's script defunctor from video 11.5, which follows from our result in ODA, the first around cohomology group. So this is corollary 5.11. So I'll call this lemma D of A. It says let A over Z sub L be an abelian variety. Now, what does it mean for A over Z sub L to be an abelian variety? That just means you're taking the neuron model of an abelian variety over Q sub L with good reduction. Okay? Then there's a canonical functorial isomorphism of F sub L vector spaces between D of A of Q bar L bracket L star 0. So remember, this 0 notation has to do with the defunctor. And cot sub 0 of A over F sub L. What does this mean? This is the cotangent space at the origin of A over FL. Okay, so let's keep going. So if we specify when A is the Jacobian of a smooth proper curve X over Z sub L, we also have a canonical isomorphism between that cot 0 A over FL we just got done looking at and H0 X omega 1 X over FL. So kind of global sections of this sheaf of differentials here. And when X, specifying further, when X equals X sub 0 of N with L not dividing N, this gives me an isomorphism of T sub F sub L modules, D J0N Q bar L bracket L star to the 0, so the thing that kind of is on the left-hand side of the lemma D of A, and S2 gamma 0 of NFL, because S2 gamma 0 of NFL is isomorphic to the sheaf of, to the global sections of the sheaf of differentials on X in this case here. So we've known that since chapter 3. Okay, so we have this kind of specifying all the way down to our specific setup, right? All right, let's consider the Galois action on V equals J0 N bracket L star bracket M, which is isomorphic to J0 N bracket L mod M star, by Mazur's Eisenstein ideal paper, proposition 2.14.2, and you should absolutely be reading this paper. It's a fundamental paper when you're studying this kind of stuff. Or by the main result from Boston, Lenstra, Ribbit, quotients of group rings arising from two-dimensional representations. Every Jordan-Holder constituent of the representation of GQ on this T mod M vector space is isomorphic to rho star sub M, which is isomorphic to rho sub M. So this here is the dual representation. Okay? And so the T mod M dimension of D of V is twice the T mod M dimension of dV0 by basic properties of the D module and this observation here. And when we talk about this, we're regarding V as a good G sub L module. Okay. However, our new isomorphism, the one we just discovered, implies that dV0 is isomorphic to S2 gamma 0 NFL bracket M, which is one-dimensional by the Q expansion principle. That is, S2 gamma A kind of dual here is a free T sub A module of rank 1, which is a standard result probably going back to chapter 3. And so D of V actually has to be two-dimensional over T mod M by that equality we just discovered above and this isomorphism. And so the same is true of V by general facts about the defunctor. And so we're done in the first case, we have a two-dimensional quotient space. Okay? So what about the harder second case? This is the case where L divides N, but L squared doesn't divide N, and T sub L isn't in frac M. So let me tell you the main steps that you have to do here. First, we're going to work with X equals X1N mod H for some H and Z mod N Z cross instead of X0N, kind of generalizing up. We'll write N equals N prime times L, where L doesn't divide N prime. Okay, so first, we may replace X1 sub N kind of as a Q curve by X1 N prime LQ, which is X1 N sub Q mod Z mod LZ cross. Indeed, the reason you can do this is because the maps between Jacobians induced by alpha from X1 NQ to X1 N prime LQ and beta X1 NQ to X1 N prime LQ induce isomorphisms on the L divisible groups localized at M. Namely, the kernels of the induced alpha and beta are quotients of H or Z mod L Z cross, but are also L groups with Galois action whose Jordan-Holder factors are isomorphic to rho sub m. This is a contradiction unless the kernels are trivial, which is exactly what I'm claiming is true. Okay, so that's kind of a brief argument, but it justifies this reduction here. Why would you make this reduction in the first place? The motivation for it is that the scheme x1n prime L thought of as a Z sub L curve given by the moduli space for triples EPC, where E is an elliptic curve, P is a point of order n prime, and C is a cyclic subgroup of E of order L, has so-called semi-stable minimal regular model, which is a good thing to have. Okay, we're not going to dive too much into that. Okay, so that was step one, is just like a bunch of reductions and then replace by an ultimately easier to work with modular curve. So let's get into the second step. So we'll call T sub m by R, and we'll let R bar equal R mod LR. And we're going to change perspective to consider V equals J1 n bracket L of Q bar localized at M. That's because of the change of modular curve. Okay. The next thing to do is to show that since T sub L isn't an M, there must be a short exact sequence of R bar bracket G sub L modules, 0 to V to the R, we'll call it, to V to the U, we'll call it, to 0, where V to the R here has all of its irreducible subquotients ramified, and V to the U has all of its irreducible subquotients unramified. So R is for ramified, U is for unramified. Moreover, you have to show that V to the U is isomorphic to homomorphisms from V to the R to mu sub L, the group of Lth roots of unity, as R bar bracket I sub L modules. So this all has to be shown. This is like what I'll call step 2 of the proof. Okay? Steps 3, 4, and 5 are as follows. Step 3 is to show that if V to the R is free over R bar, then V is also free, which will make V isomorphic to R bar squared, and it'll make R bar Gorenstein, which essentially just means, this is a word we've run into before, I think back in chapter 3, it just means that FL homomorphisms from R bar to F sub L, that's a free rank 1 module over R bar, so it's basically just R bar. Okay? Step 4 is to let, by step 1, we're going to use the reductions here, X, which is x1n prime L, let J be its Jacobian, we'll let J sub Z sub L be the neuron model of J over Z sub L, and we'll let J sub Z sub L bracket L to the T be the largest finite flat subgroup scheme of that neuron model's L torsion of multiplicative type. Remember, multiplicative type from chapter 5 just means has a tall Cartier dual. We'll also let kind of curly V here be J sub Z sub L bracket L to the T. We'll look at its Q bar L points and then localize at M. The goal, if you kind of go back and look at the theorem that we need to prove, is really to show that curly V equals V to the R. Okay, so we do all of that in step 4. Step 5 is to show that curly V is free of rank 1 over R bar to conclude, because that will show that V to the R is free of rank 1 over R bar, which will be done in that case. That's exactly what we're trying to show. Okay, so in the next video, we will sketch the proof of each of these 5 steps to conclude the proof of theorem TH, and then all it will take to finally finish the proof of proposition 4 is to prove lemma ihara. And then we will have the 4 key propositions needed in front of us, finally ready to prove R equals T in the general case. So I'll see you all then, and thanks for watching.